We're now going to talk about covalent bonds that are not sharing the electrons evenly, and we'll talk about why that might be. So in panel A here, we can see that these two hydrogen atoms are going to be evenly sharing these electrons, these two electrons, according to the electron cloud that you can see outside of the protons. Now, here we have a proton, a hydrogen, and a chlorine with multiple protons, and you can see the amount of time that, or the probability of an electron from this in this orbital versus this orbital. In chlorine, there's actually a higher probability that the electrons are pulled over to the right side towards the chlorine atom. Why is that happening? One thing I want to also point out is this little symbol here is a lowercase Greek symbol for delta. And delta is, if you recall earlier when we were talking about energy, delta means change. So this is a lowercase delta. It means partial change. So this is a partial positive charge. The electron that used to be around the proton here is kind of getting stolen from the proton by the chlorine atom. And more of its time is spent over here on the side of the chlorine. And you can see here we have a delta. It's delta negative, which means it's partially negative because the electron is over on this side more. Why? When a positive charge of one nucleus is stronger than that of another. Proton here is a single proton, and chlorine here has multiple protons. And because of that, and because of the distance from the protons here and the electrons and the shell, we have a higher pull or a more electronegative element over here. That unbalanced distribution of electron densities within a bond gives us what we call polarity. It's not a complete transfer. They're still sharing between these two spaces. It's just they tend to like this element better than the one on the left here. And again, that small lowercase delta means partial charge. Here's that hydrochloric acid, HCl. This is the way we would write it out with a partial positive, partial negative. And if we actually look at the values, the hydrogen actually gets a 0.17 positive charge. So it's not a +1, and the chlorine gets that electron, that negative charge. So it's a negative 0.17 charge on the chlorine. Polar covalent bonds are these bonds that carry those partial charges. And this is called a dipole. The two poles or the two charged molecules are involved. Polar molecules have partial charges and negative charges on the opposite ends of the bonds. And if we have a dipole moment, it's a measurement of the extent to which that bond is polarized. Here's an example of the equation we use for that. We have mu is the dipole moment, and the charge is Q on either end multiplied by the distance between them. And that tells you that measure of that charge and distance, the dipole moment. So Coulomb is typically the unit involved here, and we also sometimes use units of debye or D. It's a non-systematic unit for dipole moment. The size of the dipole moment describes that degree of polarity between those two compounds and how polar that molecule is. So we'll talk about this and give some more examples coming up here. Based off of what I told you about the dipole moment, which situation below results in the largest dipole moment? You should have looked at the biggest Q value, or the biggest charge, is going to be multiplied by the distance between the two compounds. And if we have distance separated, these are angstroms. It's a really tiny unit, but this is the closest distance. These are the two biggest charges. And so if we're taking, this is the smallest distance, this is the greatest distance. If we have the charge times the distance, we have the biggest number here. That would be E. So the distance is 8 angstroms, and separating a +2 and a -2 charge. So remember that mu or that dipole moment is equal to the charge times the distance between the two charges. So this would give us that if we basically 8 times 2 is going to give us 16. Here we have some dipole moments for various compounds, HF, HCl, HBr, HI. Looking at these, we can see that dipole moment is the largest on the top. So remember, the higher the dipole moment, the higher polarity of that bond. We can get carbon monoxide is polar and nitrogen monoxide is polar. And here are some of the bond lengths between them as well. Here's a diagram that just gives an idea of the relative electronegativity for some of the elements on the periodic table. And you might notice that the corner up here is rather high. That fluorine compound has a really high electronegativity, and it decreases as we get away from this corner. So one of the interesting things that we can do with electronegativity is kind of looking at this through as a diagonal. And we'll show you this later in the discussion here. But we can determine if these two elements are going to be electronegative based off of where they are on the periodic table. And this is just kind of gives a quantitative basis for this value between the difference in electronegativity and the estimate of the bond polarity here. To do that, we look at the electronegativity for compound 1 compared to compound 2. And the bigger that difference, the more likely it is going to be a polar compound, where we'll have a partial positive and a partial negative compound. When this number gets to be around 1.5, a little higher, that's about the percentage between ionic and a polar bond. So there's kind of that difference here. So if we're basically between that 0.5 and the 1.7, we're going to be talking about something that's polar and ionic. If we're mostly at about 50% here, so where we have a 0.5, this is mostly covalent and purely covalent, nonpolar. And then when we go above that 50% to ionic to 100%, this is going to be largely ionic bond. Using this chart and basing it on the differences between the electronegativities, which would you think is the least polar bond? So we look at the difference between H and Cl. We're at about 0.8. HF, we're closer to that 2 value. So that's a little higher, that's a little larger right now. HI, we have 2.1 to 2.2. So that's only 0.1 difference. And HBr, we have 2.1 to 2.8. That's about 0.7. So the smallest difference is between 2.2 and 2.1. So we'd say that is a normal, if those two things are bonded to each other, that's going to be a normal covalent bond without very much polarity at all. We are going to come back to polarity in a little bit, but now I want to come back to the Lewis structures. And we're going to take all of this information, we're going to start to draw different types of compounds using this Lewis structure technique. So it's a way to draw diagrams of different compounds, and we can use this Lewis method to make a good, accurate prediction of what the shape is going to be. For example, here is silicone. We know that it has 4 valence electrons, and we're going to look at fluorine here has 7. So we can combine these to create this 4 different bonds with silicon. And we're going to discuss in the next section a little bit more, the next chapter. We're going to talk about shape a little more. But this just kind of gives you an idea that silicon's kind of the center compound, and then we have 4 fluorine compounds coming off of that. So the method is to first decide how many atoms are bonded to that central atom, and the central atom usually is given first in that compound formula. So it's the least electronegative element is typically shown first, and that also correlates with usually how many things that need to bind to it. We're going to count all of the valence electrons. So for all of the atoms, all of the valence electrons, we don't want to lose any of those. Those should be somewhere within the molecule accounted for. And then we're going to determine how many electrons would need to be filled out in the octet. And that should be equal to the number of bonds that will form. And finally, we'll look at formal charges to determine the number of electrons that belong to each of the different atoms. And it should be the same number of valence electrons that we started with at the beginning. So here is an example of silicon trifluoride. Now again here, we are only accounting for valence electrons. We're not looking at the internal shells of these elements. So silicon, for example, has just 4 electrons in that outer shell of itself. And since we just have one of these, we have 4 total valence electrons. We have 4 fluorine molecules. Each fluorine molecule has 7 electrons. 4 times 7 is 28 total valence shell electrons on the outside. And we have a total of 32 electrons. So how many more electrons does each need to fill for an octet? Silicon, right, has 4. If we have, it needs to have 8 total. And that means that silicon needs to find 4 more electrons from somewhere. Each fluorine element needs 1 more electron each. So we can fill up the orbitals here by completing now we have silicon is bonded to each of these different fluorines. So silicon gets 4 more. The silicon's donating 1 to each of these fluorine. And then we can also count how many of the electrons are left over. So we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 24 lone pair electrons, and then we have 24, 25, 26, 27, 28, 29, 30, 31, 32, which gives us the total number of electrons that we started with in the valence shell. So that means that we did our accounting right. We put together a good example of a solid Lewis structure. Drawing Lewis structure holds really well for second row elements like carbon, nitrogen, oxygen, and fluorine. So this always works for these. And part of the reason that this is done, these are very common elements in the periodic table that are part of organic compounds. So this works really well for these. But when we get outside of those elements, we start looking at boron and beryllium. Sometimes those can have less octets, and we can talk about that later in the semester, but these are some exceptions to the rule at sometimes. Second row elements can never have more than 8 electrons. However, once we get to the third row and below that, those often can exceed the octet rule. And the reason for that being able to go in the third row, remember in the third row, in the first row, we only have s orbitals. In the second row, we have s and p. In the third row, we have sp, and then we've added the d orbitals. And the d orbitals can play tricks on where electrons can go. And so we have a bigger element. We have some extra places that we can kind of move and exchange electrons. So that can change how many electrons an element is able to take into itself because of that d. The d orbitals can sometimes play a role in some of that chemistry. But we're not going to focus on that right now. We're going to just do some simple structures with Lewis diagrams right now. One example I want to start with is this H2CO3 compound. And the first step again is let's look at all the valence electrons for each of these elements. And using the periodic table, you can count from the right starting at 8. And then you can go 7, 6, 5, and 4. And you'll see that carbon is matched up with 4 valence electrons. Oxygen's matched up with 6. And then hydrogen is kind of on the other side of the periodic table. But you should be able to know that that also has 1 valence electron. How do we get these elements to 8 electrons? Well, carbon needs 4 more. Oxygen needs 2 more to get to 8. And then hydrogen, remember that one is not ever going to be 8 electrons. It will only get 2 total. So it can only have 1 bond each. You'll only have hydrogen having 1 bond. There's not an instance where you're going to have to deal with something where hydrogen is going to be double bonded, for example. So it's just going to have one bond always. I'm going to start with carbon, and I'm going to kind of make these 4 different sticks coming out of here, kind of to represent that I recognize this needs 4 more electrons. We're probably going to start with, we're going to create 4 new bonds, right? But really only these blue sticks right now only have 1 electron in them until we combine them with another one. Oxygen has 6 valence electrons, and I'm going to point these 2 openings with blue, kind of blue sticks as well, to kind of recognize that this blue thing, it's a really, right now, just a 1 electron. It's going to have to connect with somewhere else, that we're going to have a blue stick so that we can organize these and combine these. Remember, we have 3 of these. So this is H2CO3. We have 1 carbon, 3 oxygens. Here's the 3, and then 2 hydrogens. So we'll do 2 hydrogens. Also, we're going to have, because they need 1 more electron each, we're going to have these spots. So now we basically just try to combine these so that we can overlap these different these lines with different elements. Usually what we want to do is we want to start with the most electronegative element and start adding things to that element first, because that's the least electronegative element, which means that it's probably going to be bonded to the most number of things. So this would be, we would usually use this as our central atom and then build off of that. Here's an example of how we can put that carbon in the middle and then bond it to different things. But one of the problems that we have now is that carbon would only have 6 electrons in this state. And this wouldn't be something that we would want to do. So we're going to have to move something. And remember where we have those lone pair of electrons here that I am not showing you above here. That's why it's actually helpful to keep track of these extra valence electrons as lone pair electrons so that we can keep track of those. If we know that this has 8 still here, but this only has 6 electrons, here we have 2, 4, 6, and 8 in the bond, but right now this carbon has 2, 4, and 6. It's missing electrons. But we can do something. We can actually share this element because it has too few electrons. So then we can move these electrons down and share these. And now let's count how many all of these elements have. Right, hydrogen has just 2, which is fine. This oxygen has 2, 4, 6, and 8. That's great. We have an octet. This carbon has 2, 4, 6, 8. Remember, this means it's a double bond, which means it has 4 electrons in it, 2 sets of 2. So that's 8. We've got an octet. This is a mirror image of this side, but we'll just count anyway. 2, 4, 6, and 8. That is great. We have hydrogen has 2 electrons, which is all it can have. And then this upper oxygen has the 4 from this bond, this double bond, 2, 4, 6, 8 for the lone pairs. Excellent. So we're at 8 electrons for all of our second row elements. The hydrogens have 2. We're all filled up, and that is how you would make a reasonable structure starting with a chemical formula. We'll do one more example of these where we have nitrogen, dinitrogen, difluoride. Nitrogen has 5 valence electrons, so we need 3 more to get to 8. Fluorine has 7 valence electrons. We need 1 more each to get to 8. And this is how I'm going to draw this out. Apologize here, I'm missing the 2 electrons on the fluorine here. So we'll add those. And right, so we have the 1, 2, 3, 4, 5 electrons. And these where I have the kind of lines, I'm just showing that because I'm saying that there's a lone pair, right? Sorry, these are the lone pair. I just have 1 carbon that's going to need a bond, and it's going to need to connect to something. Same here. This is just a mirror image of this nitrogen. Fluorine, we have 1, 2, 3, 4, 5, 6, and then this is the 7th that we're going to have to pair up with something. 2, 4, 6, and the 7th that we'll have to pair up. All right, so let's try some different options here. We're going to have the skeletal structure. We can, remember I said the least electronegative, so the furthest left on the periodic table. This would be nitrogen in this instance. So let's bring that into the middle. If we bring these together and start with those as our core of the structure, and then we can pull those fluorines on the outside. Let's make sure that this structure makes sense because now we have the fluorine has 2, 4, 6, and 8 in the bond. We have 2 and 4, okay, and 2 and 4. So nitrogen, we're missing those lone pair that we had previously drawn out, and we have these two other here. So let's make sure that we have the electrons where they need to go. This fluorine's fine, this fluorine's fine, but there's something not quite right that's happening in the middle. So we have this one electron from this pair as part of this nitrogen. We have one from this this interaction, this bond. So we have 2 from these 2 bonds, 3, 4, 5. So that is the total number of electrons that we started with. And this fluorine has the one that it started with. This fluorine has this one that it started with. So the 5 electrons here, but we don't have an octet. So we have the total, when we're talking about the octet, we're talking about the total electrons that are associated with only it and also that are being shared. But here we have 2, 3, 4, 5, 6, 7. So we're missing an electron that needs to be shared. And that's the same as this nitrogen here. All right, so how can we create an octet for this current structure? Well, there are not enough electrons in this form. So what we have to do is actually create a double bond between the nitrogen atoms to satisfy the octet. So we take these lone electrons here and we combine those to form a new bond between the 2 nitrogen elements, and then we can create a double bonded nitrogen here. So this would be a good structure now because we have an octet here. We have the 2, 4, 6, and 8 from the nitrogen, and then we have 2, 4, 6, and 8 for this nitrogen, and we have the 2, 4, 6, and then the 8 in the bond for that fluorine. So now we have satisfied octets for all of the elements in this compound. That would suggest this is a good structure. I wanted to show you an example of an exception for expanded octets. Remember the d orbital, we can go to that 10 electrons in the d orbital. Once we get past this second row, we get to the third row, they do have access to these orbitals, these 3p orbitals. They do have access to the 3d orbitals, and they're not too far away in terms of energy level. And here's an example looking at phosphorus pentachloride, PCl5. We have 5 valence electrons, and I'm showing you that I'm drawn out here. 1, 2, lone pair, and then we have 3, 4, 5. We have these 3 that need to pair up somehow. We have chlorine with 7, so we have 3 pairs of lone pairs, and then 1 that needs to pair up. So we have 5 of these chlorine elements and a phosphorus. So we can start to piece these together. We can combine those and make those bonds, but then where do the extra chlorine go? And the actual experimental data, this is an actual molecule that can form phosphate pentachloride. We actually have, this is what happens. Phosphorus comes in the middle, and it's actually bonded to 5 different chlorine elements. So we have 2, 4, 6, 8, 10, which is crazy because that's 10 electrons, right? That's more than an octet. But again, those electrons can go into the d orbital. They're higher energy electrons. Just because something is higher energy doesn't mean it can't happen. It just means that it requires more energy, and those bonds are higher energy bonds, which means when we break them, they can release more energy. Expansion into the d orbital can allow, for example, these 5 bonded elements. We can do 5, we can do even 6, and that's about the extent of what we'll be talking about anytime in this class. Another exception is boron tribromide. Here's an example where we have boron will have 3 valence electrons, and technically to get to 8 it would need 5 more. Bromine has 7 valence and it needs just 1 more bond. Here we're going to have, if this compound exists, boron tribromide, we have this boron with 3 electrons, the bromines with the 3 pairs of lone pairs, and then 1 electron that needs to be paired up. Well, it's kind of nice because these electrons here need to be paired up as well. So if we just kind of add those together, we get this structure. Now the problem is what is happening. We have 2, 4, 6 electrons in here. Where are those going and how does that work? Well, we can actually have the electrons are expanding into the p orbitals and there are none in the s orbital. So we're filling p orbitals here. Again, they're a higher energy orbital than the s orbital, but just like how we could do that with the phosphorus and bump those into a d orbital, which are higher energy, we can do the same thing with p orbitals. Again, these are a little higher energy electrons, but that just means we get more out once we, if we break those and reform into new bonds. So just a few different odd examples where the octet rule doesn't apply. When we look at the periodic table, we want to recognize that we are starting with the s orbitals. Here are 1 and 2, but the p orbitals start with 2, and then we go to 3. And if we go to the s orbitals, we're going to be in the 4, but then we go into the 3d orbital. So the s orbitals start with 1, the p orbitals start with 2, the d orbitals start with 3, and actually when we get down to the f orbitals, those start with a 4. And this is just kind of how that works. Remember, we talked about the principal quantum numbers, and it's all based off of that idea where the larger that shell is, the more different options we have for the orientation of those orbitals. All right, so now we're going to start looking at formal charge for these compounds. So how many valence electrons does 1 nitrogen and 2 oxygen atoms have? And how many are shown in this structure below? So I just want you to take a second, count the valence electrons. How many are they supposed to have? How many do they have? And then we'll kind of go from there. Okay, let's do some accounting. So normally oxygen is going to have, if we look at oxygen, would have 6 electrons. Normally, this element has 1, 2, 3, 4, 5, 6, 7, 1 in that bond. So now we have 7 electrons. For this nitrogen in the middle, we have 1 in this bond, 2, 3, 4, 5, 6. So here we have 6 electrons. Normally nitrogen has 5 electrons on the periodic table. And then when we're looking at the final oxygen on the right, we have 1 electron here, 2, 3, 4, and 5. Again, for oxygen, normally has 6 electrons. Now we have 5 electrons. So normally we're going to count the 6 here in this oxygen and the 5 and the 6. So under normal conditions, that would be 17 electrons. However, in this instance, in this compound that we have generated, we have 7 plus 6 plus 5, which would be 18 electrons now. So what does that mean? What is the formal charge of this? So each of these elements should have a different number, should have the same number of electrons associated with it. But since this oxygen actually has an extra electron, it has an overall -1 charge. So that oxygen has a -1 formal charge on it. The nitrogen in the middle, since we have 1 extra electron than it would normally have, where we have the 6 electrons and normally would have 5, that means that it is going to be also a -1 charge. And then finally, so it'll have a -1 formal charge. The oxygen on the right side normally has 6 electrons. Now it only has 5, so this is going to be a +1 charge. So we're going to have a positive charge. The overall charge of this molecule, if we take the minus and the minus and the plus, is going to be a -1 charge for the overall molecule. And it's a contribution of the formal charge of a -1, -1, and a +1 here will give us the overall charge of a -1. So we'll look and see if that makes sense, or if we need to adjust. This formal charge is going to tell us something about if the structure that we've made, the Lewis structure, makes sense, or if we should adjust it and fix it. So is this the right structure or not? Let's look more into that question. Let's start with our 5 valence electrons. So here we have 1, 2, 3, 4, and 5. And with oxygen, we'll have 6, so we'll have 2 lone pairs, that's 4, and then 5 unpaired electrons. And we have 2 of those. So that's the starting point here. And the first step would be to then bring those together. And you kind of see here, I'm going to just take these 2 electrons and combine them, and then this one and that one, I'll combine them into this new structure. where we have now the nitrogen's the central atom, the least electronegative, the furthest to the left, needs the most bonds. So I'm going to provide multiple bonds to that as the central atom. Now we still have some unpaired electrons. We have an unpaired electron here, an unpaired electron here, and an unpaired electron here. And so we still should kind of add some of those together. So let's just take these two and combine those into a double bond now. And here we'll do that. And let's also pair up the electron here with the nitrogen and the oxygen just so that those are together as well. And we'll just move the electron instead of making a double bond. We'll just move this into the outside. Now let's do the formal charge accounting again with the oxygen. So normally we have 6 electrons, and bonded, what do we have here? So here we have 1, 2, 3, 4, 5, and 6. When we're looking at determining the formal charge, we only take half of the electrons in that element. So 1, 2, 3, 4, 5, and 6. So bonded, this also has 6 electrons. So the formal charge for this compound, for the oxygen specifically, would be 0. For the nitrogen, normally we have 5 electrons. How many are in here? We have 1 from this bond, 2, 3, and 4. That's 1 less than we normally would have, so that would be a positive 1 formal charge. Now with this oxygen down here, we have, normally we start with 6 electrons, and here we have 1, 2, 3, 4, 5, 6, 7 electrons. Formal charge is a -1. So the overall charge is 0, which is good, which means that we don't have a charge that's associated with this. The only problem is that we have this lone electron, on the nitrogen. So it is a little weird that we're not able to kind of allow for this to, kind of go somewhere and create an octet. A lot of times NO2 will be an ion. We'll add an extra electron in here to fill up and complete this orbital here. But in this case, we're just looking at NO2 not as an ion. One of the interesting things that we can do with this element is actually we can move these around. Since this is symmetrical, we could take the electrons here and make a double bond here and move these electrons up on top so that there are 3 lone pair like there are on the bottom. So you can see I'm going to do that with these arrows, moving the electrons up to create this other element. That is really this idea that we're going to look at next called resonance, and it's a way to explain how we can have multiple equivalent Lewis structures and the fact that the electrons can actually move in and throughout this whole molecule. And I think that's a good stopping point for right here, and we'll continue the resonance idea and formal charge. We'll get into that a little more detail in the next lecture.